All right, here we go. Lesson 6.3, the least squares regression. Now, in our textbook, they refer to this as LSR. Sometimes they might talk about the LSR line. Sometimes they might talk about the LSR equation. So, in the old days, when you were back in Algebra 1, we called it the line of best fit. So know that if that comes up in the directions, you're looking for the line of best fit. So you're going to enter your data into, hopefully you are familiar with Desmos. The data will come in like 2 columns. And normally, this will be the explanatory and this will be the response, meaning this is the X and this is the Y. Okay? Think about it for a moment before you make that decision. Remember, Y must be explained by X, right? So in this case, we're saying that the dog years, right, help us calculate the human year equivalent, or vice versa. In this case, it really wouldn't matter which way you did it. Either way would be significant because one doesn't necessarily depend on the other. Okay? All right, so open up Desmos and you're going to type that in. So I provided a link for you in Schoology where you're going to go back and open Unit 6.3 and then click on the Desmos link for doing homework. All right? Now, don't mess with this one right now, but know that this is where you're going to be entering your information in the table on the left there. Yeah? Don't change that right now because that's actually going to help you do the first assignment in your homework. All right, next, once the graph is done, it's going to give you a picture. Desmos might look something like this when I enter the data for the dog and the humans years. The one that's provided to us looks like this. It's a little bit flatter. The axes have been adjusted. So create a sketch, doesn't matter which one you choose. Don't bother with a line, just the dots, okay? And so we need an axis for our sketch, for our drawing. Make sure you label. This would be dog years, and this would be human years. Second, it'd be nice to have some numbers, one number on each scale. So if you look at dog years goes up to like 11. So I think I'm going to put over here something like 10, right? And then I'm going to go up to 60. And I don't need to break up the scale, but I just need to have a value, right? All right. And then I'm going to now sketch out what I see. This is what you see, yes? So just put some dots down that kind of mimic that same pattern. And we have something like this, I think. Don't worry about quantity, just the general shape. You're done with the sketch of the scatter plot. Next, your software, Desmos in this case, is going to report to you R. What is R? R is the correlation coefficient. Some nice background music going on there. And then it's going to also report to you an equation. So let's go look at Desmos and to see where those are. Now this isn't the Desmos, but we see it reported over here. This is a different piece of software. Desmos is going to report it to you down here at the bottom. Yeah? Okay, so a couple things. Make sure you report R, not R squared, right? Okay, and then our equation is right here, but notice the values are sitting down here, M and B. Okay, so I would suggest you round these numbers off. So the B, which is the y-intercept, is 7.8. And M, we could say, is 4.6. R, we're going to report as it is, 0.99 Okay. All right, so R, 0.9907. Close to 1. Very strong relationship there. Our equation. Why do we put a little thing on top of the y? No particular reason. This is how stats defines their least squares regression equation, is that it's not a normal y, it's a special y. So we put a little hat on top of it. And again, the a value was the intercept. I have forgotten it already. 4.6, no, 7.8. All right, so 7.8 x, no, 7.8 is the y-intercept, plus the slope, 4.6. Gosh, I wish my memory worked better. Whoops, not n, x. X is just normal, no, nothing on top of that. So here is our line of best fit, our LSR line equation. All right? In our software, you can get the line to show up if you click on that little button there. When you highlight that button, then that line shows up. All right. Next, before you say, hurrah, this is a great equation, and start using it, we need to verify that it's okay to use. Remember yesterday we talked about the 4 things that we need to check. Number 1, is the graph, whoa, something's happening there. Linear. Is the graph linear? Are there any outliers in my data? Is my sample size large enough? Sample sizes of, let's say, 5 are too small. Here, our sample size is about 10, which is still smallish. We don't want to get crazy with these types of numbers. That is, we don't want to be too excited about our R values, but we certainly, it's fairly valid. Notice there's no outliers, and notice my graph looks linear. Okay, so everything seems to check off. Don't forget about the last thing, and that is make sure your variables are not homogeneous or homogeneous. Maybe that's how I should be pronouncing it, not too sure. Anyways, so check those 4 things before you start using the equation. After all, this is why we build an equation, so that we can use it to predict new values. You say, what new values do we need to predict? Well, if we go back to our chart, we can see there's a gap here. There is a gap here. Okay. There's also gaps on either side. Caution on those. We'll start with the ones internally. For example, what is the relative age of a person with a dog that's 6 or 9? So I'm going to pick 6. Now what this is called, this first type of prediction, is called interpolating, or to interpolate. So if I have a 6-year-old dog, which I do right behind me, actually on the bed, being very quiet and good, I'm going to replace the x value with 6. Why the x value? Well, because if you look back at the equation, remember how we set it up initially? We said dog age was x. Okay. So I then go to the equation, and remember the equation said y hat equals 7.8 plus 4.6x. So y hat equals 7.8 plus 4.6 times 6. And I'm going to do that on my calculator, and I get 35.4. I'm just checking that right now, making sure my memory works right. Correct. So we can now conclude that a 6-year-old dog equivalent age in human years would be a 35.4-year-old person, human. Now, let's say your dog was older than that. Let's say your dog was 13 years old, an older dog, one that's been around the block a few times. Well, now this is actually extrapolating, not what did I call it? Interpolating, but extrapolating. Why? Because notice the gap that we're looking at in this case is 13, and that's way the heck out here. That is beyond my window of data. So that's called extrapolating if I go on either end and pick values that are beyond. If I'm inside my data set and I'm finding values here or here, that would be interpolating. Okay. All right. So then the final thing, if I plug in 13 and I get y hat to be 7.8 plus 4.6 times 13, and I think we get something like 76.4 years, I believe is what I had. So maybe that was 76.6. So this is kind of dangerous to do because we are extrapolating. We're safe when we interpolate. Solid ground. Here, not so much. Yeah? This is unsafe, hazardous. Be careful. All right. And again, how do you do this? You just plug in the values into the equations. Plug into equation. All right. One note here at the bottom. Note that these two graphs down here at the bottom, very similar. They're data sets, right? If you look at them, they're very similar. The line of best fit is very different. And notice the R value, 0.94, 0.316, right? This, good. This, not so good. Why? Because of that data point there, right? It was up here, and now it's down here. So supposing somebody entered a value wrong, that's going to drastically change your set, especially when you only have 6 data points, and that would be 7. So caution, again, that's just showing you how sample size can drastically change something with an outlier and make it look really non-linear. So careful on that. Last thing I want to do before I walk away from this is they may ask you to interpret your slope. So let me do that. What does the slope mean? Slope, you recall, is a ratio of the rise over the run. So if you look at and ask yourself, which variable is the rise variable? Which variable is the run variable? Hopefully you remember this is the y's and this is the x's. So if I go back over here and look at my data set and say, okay, yeah, the y was the human and x was the dog. So then if I come over here and I say this is 4.6 human years versus 1 dog year. Yeah, that's how I interpret my ratio, my slope for the, again, LSR line. Good luck with your homework. Hopefully you are able to do those problems there using the software Desmos, remember. Plug in the data, report your results, interpret your answers, use your equations.